Hello world. Thank you very much for joining in to my next stream, Let's Code. We will still stick around like the last two times, stick around with Roslyn, but this time we are not doing analyzers. This time we are doing source generators. They have been initially added with Roslyn 3.8. That is within the .NET 5 SDK. There's also two new C#9 language features that we will have a look at, which facilitate source generators. And we will check out different source generators, how we can build them, and how they have evolved over time, well, over the last 2 years. And we will then have, so we will see the difference between a source generator and an incremental generator. And at the end, we will then modernize a source generator, which has been built with Roslyn 3.8, which is the .NET 5 SDK, and modernize that to using Roslyn 4.0 incremental generators, which is the .NET 6 SDK. So let's have a look at our agenda. First, we will see what's a source generator, when and why we want to use source generators, what is the big benefit. We will see what the limitations of generators are. There are some rules to them. Have a look at two new features in C#9 which facilitate source generators. Then we're gonna check out some examples of source generators. Now with the .NET 6 SDK, there have been, well, not with the .NET 6 SDK, but with .NET 6, there are some generators included. We will have a look at the system.text.json generator, which is included in .NET 6. And we have a look at the logging generator, which is included in the Microsoft extension logging abstractions package. So you get them in, for example, in a worker or an ASP.NET Core application per default. We will see how we can test source generators and then have a look at the source code of how we can build a source generator. So we will write C# code that actually generates C# code. So that's metaprogramming. We will then see what has been added in Roslyn 3.9, and then we'll see the incremental generators. That's the next step in source generation, and what their big benefit, but also a bit of a drawback is compared to 3.8 source generators. And at the end, our live coding will then include, we will modernize three 3.8 source generators to 4.0 incremental generators. So what are source generators? This is the official documentation from Microsoft. A source generator is a Roslyn component that we can write ourselves when we create ourselves basically an analyzer project, since generators are technically speaking analyzers in .NET. And we can then pack them in a NuGet package, and others can then consume our generators. And the generator then hooks in to the compilation. The generator then receives the source from the compilation step, which is the syntax tree of the user code or of the source generator consuming project, and adds also the compilation on it. So we also have access. We can via the compilation we can get the semantic model, just as we did the last couple of times, the last two times with analyzers, and can then ask against the source tree semantic questions, whether that string represents the system.string, or maybe a different string. Maybe I wrote my my custom string. And then at the end, the source generator then basically produces, again, new source code. And it really is basically text. Just as we write our CS files, the source generator writes CS, not files, but, we can put them out and have a look at them, but basically just produces a string, feeds it back to the next compilation step, and then the combined original user code plus the source generated code end up then being the final compilation result, which then ends up, for example, in the application that we run. Now, why would we like to use source generators? So source generators can actually, let's jump back to the documentation. The documentation says this as well. They highlight the common scenarios to avoid reflection. So when we would like to, or up to now, without source generators, when we want to dynamically, for example, I'm a library author and I want to do serialization, for example, supply some serialization package which serializes to JSON or XML. And then we want to have a look at the type that the runtime type that the user code defined, and then at runtime via reflection we can then have a look, okay, what properties does this type have, and then create according XML or JSON, and also have a look at the attributes that are placed on those, for example, properties on these types. But this is all done in runtime, so this costs performance. Now, what a source generator can do can actually switch, take this runtime part, or this runtime reflection of the user code into a compilation step. So we can have a look at the user's code at compilation time and then generate very efficient code, which is then faster at runtime. So we can avoid or at least reduce reflection. What you can also do is reduce tedious implementations. For example, a I-equatable implementation looks always very much the same. Just as, well, if there wouldn't be something as, let's jump to SharpLab. If there wouldn't be something as a record just yet, we could do basically something similar. I will now define a record. Let's do a record class, my record, pass in a number, int number string text. And this now basically creates a class, there it is, which implements the I-equatable. And this I-equatable implementation now should take both properties into account, the number and the string, but also check if the type is equal, so the my record type. And basically, I already know what the I-equatable implementation should look like. And then we could generate this like a record. Well, this is a language feature. The analogy is not perfect, but we could, for example, write a generator which automatically implements these I-equatables. Where is it? For example, here, so this equals calls, so the object equals calls into the strict strongly typed equals from the I-equatable interface. And here then we check if this is indeed either already reference equal, but if it's not reference equal, then we see if basically we have a look at the backing fields, if the backing fields of both properties are equal. So a record doesn't have reference equality semantics, but actually value equality semantics. And then also overloads both equality operators. And for example, we could also do something similar with source generator. So where we already know the scheme of how the implementation would look like, but then have a source generator created, so we don't have to write that code manually, and we also don't have to test that code manually, because the generator is already written and tested, so we can avoid tedious or repetitive implementations. For example, another use case would be iNotify property changed for MVVM styles applications. And we can build source generators with Roslyn. So it's very similar to building analyzers, and can then create very efficient code that then the user can consume, for example, then without reflection or avoiding allocations. Now, what are the limitations of source generators? The thing about source generators is they can only add new source. We will see there is a method called actually add source. We cannot change or remove existing source. So this doesn't replace something as IL weaving, which would really replace stuff, but this just can add on top of that. For example, and now this pairs now well with the new C# key features. For in C# 9, the partial method has been enhanced. Previously, a partial method didn't necessarily had to have an implementation, but the limitation was that they must be void. They can't have any out parameters. So they basically are some fire and forget methods where the code, if this partial method hasn't been implemented, then actually doesn't really exist, similar to a conditional. So we will see those are the previous limitations. It couldn't have an access modifier. It was always implicitly private, so that other code, for example, another library, another project, cannot call into that code. It must be turned void, because a partial method up to now didn't need to have an implementation. It could have an implementation, but if there is no implementation, it basically gets stripped out, and this is why those limitations exist. Also, there can be no out, so we cannot have source level side effects kind of thing. But now with C# 9, this limitation has been lifted. Basically, this all is now allowed. It can return void, it can have out parameters, and can override it and such. And this new rule applies is if we explicitly state a visibility, an accessibility. So when I say, for example, internal or public, then the C# 9 rule applies. If I don't state the accessibility, then the previous rules applies. So this is how backwards compatibility is achieved. Actually, let's show this in action. So I have here a small project. And here, if I zoom in, this, and here we, for example, can now define, so we have a partial class, and this partial class now can have a partial method, which is public. So this is now possible. It couldn't be done with C# 8 or before that. So if I remove the explicit accessibility modifier, now the old rule applies. And the other feature is the other C# 9 feature which was added is the module initializer attribute. And with that, we can have, let's check this out live, we can have code that we put on the module initializer. We can put this on a method, It must be a static method. This method must also be void and can't have any parameters. And this then is, this method is called initially when the module loads. I'm actually not aware what the difference between a module and an assembly is. So I think for me, I simplify it down when the assembly is loaded. I guess this is not 100% correct, but this worked for me so far. And this is now called, although I have no, if I try to see any usages of this, there is no usage of this init method. It's called by the runtime. So we set this text to initialized, and then put it out. Can you return here? Oops. To only see that. And if I run that code, we should see that this initialized is actually called. I'm not sure what I'm doing wrong. Give me a second, please. So let me try to run it in the command line. .NET 1. Okay, not sure what I did wrong, but there it is. So this initialized, this is really set by the, we never call this init method. Actually, I will rename this init method to something else. I don't change any other code, just rename the method and add here a ABC at the end. And when I run this application again, we now have initialized ABC, and it still compiles. I have no code which actually invokes that method. So we can use module initializers to, if we want to have some assembly-wide initialization, module-wide initialization in our code. Perhaps a source generator could require some static fields, maybe for a cache, to be initialized, and then have this done in a module initializer. So now let's have a look at some source generators which have been now shipped with .NET 6. So source generators are available since .NET 5, but now the .NET team is actually, the BCL team is actually creating analyzers with them and shipping them. So one of the included generators is the system text JSON generator. What we can do is, I defined here an entity. This entity has a name, it has a number. And when we now want to serialize or deserialize it, we can define our own class. We must define this as partial, which now gives the source generator the opportunity to add new code to this partial class. We will derive it from JSON serializer context and put in the JSON source generation option attribute on top of that. Now this options attribute allows several options, which then the source generator is aware of and then generates the code differently. For example, we can set the default ignore condition, or what we do here is actually we want to write the JSON indented. Then we define which type this generated serializer should do, and then we get a lot of code. So I only write one partial class, put a bunch of attributes on top of it, and then what we get is, if I now scroll up to the usage, here we now actually initialize this new entity. We then serialize it. then the JSON string, we also deserialize it and see if the round trip then works, and we indeed get back this entity instance, or at least an equivalent to it. And we pass in now from the serializer context. This is class that we have declared below, this partial class. There is now this default property. But this default property, we have not written it. The source generator wrote it. So if I have 12, this jump into definition, we will now jump to generated code. We see at the top, this is now a file .g.cs. The .g indicates that this file is generated, and also by default, well, this can be configured per analyzer, but the general rule is that an analyzer shouldn't analyze generated code. Maybe because the generated code may violate some coding styles, but we don't have access in writing this code. The generator creates it, so analyzers shouldn't produce diagnostics on that. And we get a bunch of code, and there is more. When I have 12, the entire type, then we see here a bunch of files being created. Well, it's not files, but we can, during the compilation for usability, so this file basically doesn't necessarily physically exist, only in memory. There is a way we can put this out into physical for debugging. We will have a look at this. And there is a bunch of files generated. So there's a lot of code generated, which now serializes and deserializes the entity as efficient as possible. So there is no reflection, and also, I guess, avoids a lot of allocation to have very naive but very efficient code. And as a consumer of the generator, don't need to maintain all of this code. And let's run it. Did I close? Oops, I closed the terminal. So let's .NET run. And well, we still see our ABC from before. And we have here indeed in the round trip, we get back this entity where the name is generation and the number is 1. So this is the log error that we have here. So yeah, with that, we can have very efficient system text JSON serialization and deserialization. And the other analyzer, the other generator that I've basically kind of shown is the one for logging. So when we do logging, let's jump to the documentation that explains it very well. With Microsoft extensions.logging, there is also it's called high performance logging. This is when we use, where's an example, the logger message.define. So we don't use the iLogger instance and all those extension methods that are defined there, like log error, log warning, directly, but we define a message that we log already, where we set the log level, we set the event, the message. Potentially, we could also have an exception be passed in. And this then creates a little bit more efficient and also a little bit more correct logging, because usually I tend to forget if I do a debug log, we should actually check in an if check to, if we have something like this, so we shouldn't do logger.log debug and then have our my debug message, but actually also always wrap this in an if. saying if logger.is enabled and passing in the log level debug. Because what we could have is also, let me put a template in here. I see number, and I pass in the number 12. Let's add another one, another, and 0. And if we would have this if check, we would always pass in the string and allocate here. So what we see here, there is a params args. So how those extension methods, those log debug and log critical, and all of them are implemented, they, if I have a look in the code, they have a params object array, which means, let's have a look at this in SharpLab. If I define here a public void method, let me comment this out for now. Actually, it needs to be in a class, public class, my class, and we put in my method, which takes params, this params object array. And then now let's invoke it. Public void, I call it caller, and the caller now calls into this method with 1, 2, 3, 4. Now we see that what actually gets created by this is we create this object array. Since this params, this is a C# feature, but we actually have to pass in this object array. The thing is now we always allocate this object array, and additionally we have boxing here. We pass in integers, which are value types, into a object, which is the reference typed type. So we have boxing, and this allocates. So we have basically multiple allocations. We allocate an array, and we have those more or less hidden allocations through boxing. And if I jump back to the source now, if this log debug would be disabled, I would still have these allocations here, which, although maybe I have the log level 2 set to critical, so those logs would never be put out. But I would still have these allocations because the code passes there, which is bad. So we should always guard loggings which allocate where a logger is enabled. Really check, is it enabled? So now if I have a higher log level, then I won't allocate these object arrays. And basically the log message define also takes care of that. So that was there was not a lot. So we could now have, so this is one of the reasons of the logger message. But now always writing this logger message, we need to define it first, put it into a variable, and then consume this variable is a bit, well, it's a bit more code. And we could have a generator define that for us. And this is the other generator I want to show, the logging generator. So let's get rid of that. What we can define now is we can have a static partial class, and we put in the logger message attribute on top of that, where we can still, very similar than with the logger message.define method, we specify the event ID, the log level, the message format. We could also have say that with an exception here. And then we see this method again. It's partial, but it compiles. If I wouldn't have the generator in place, now this wouldn't compile because we explicitly declare a public partial method. Now the implementation must be available. So without a source generator, this wouldn't compile. But with the source generator, basically picks that up and understands, okay, I need to add something. So when f12 is, now the source generator is generating exactly what we saw, what we could do via the logger message define manually. We define this logger message, store it into a field, it's up there, and then have this method guarded by the if logging is enabled. So we could reduce those 1, 2, 3, 4, 5, 6 lines into just 3. And we could have one partial class where we then define all of our messages. Let's define my other message. And so there is a lot to this generator. This doesn't necessarily need to be this instance. So it has different means. There is different ways of how to generate it and how to use the generator. So this is how we could then reduce. And if we are not using this if debug already, then also improve performance of our logging with less code. So that's less code we need to maintain and also less code we need to test. And this is then especially the partial feature of C#9. This is how then now source generators have gained a lot of power. Hello, Deflux. Thank you for your message. You never understood partial. I never used it. I never used it up until the source generators, and now I use them everywhere. So perhaps maybe I should have led with this. So what does the partial keyword do? It enables us to have a definition of a type or a method on multiple places. So I should have led with this, but let's define my public class, my class. Now what I can't do is define another class, because now we have 2 times a class with the identifier my class. Doesn't work, which is what. And if we put the partial on it, we need to put it on both of them. Now it's 2 different definitions, but they then actually get kind of merged into one class. So there's just one class. There isn't 2 my classes, only one, but we can split up the implementation of this class in different locations or also different files. But this all has to be within one assembly still. So this is also now an interesting fact that the source generator adds the code to our assembly, to our compilation, not somewhere else. It's then part of our compilation. So if we would publish this code as a NuGet package, the code that the source generator creates is then also part of this package. Not the generator itself, but the code it produces. Because generators usually are development dependencies. There should be no transitive dependency on them. So a project which depends on a project which uses a generator shouldn't transitively also depend on the generator or with analyzers in general. And now I could now have like the constructor here and my properties over there. And so I can split up implementations. If I have big classes, big types, we could, for example, maybe have, if we have different implementations depending on an operating system, we could have in one file the Windows implementation, in one file the Unix implementation, or similar. Or if a type is really, really big, then have, for example, part of that file, a part of that class in one file, part of the class in another file. Actually, maybe, so they would have different properties. Yes, they would have, I cannot define the same property in a partial class in both instances, because what's basically happening, it's merged. So the result will be a public class. So in the result, there is no partial. The partial will basically evaporate, and the result will then basically be both of them merged into one, which would now mean I have this int type property defined twice, and this just doesn't work. So yeah, partial classes or methods then get merged. And with a partial method, I can have the definition at one place. I could say public partial void my method, and then supply the implementation. We see what I showed before. Now this doesn't compile because the partial method void method must have an implementation because it has an accessibility modifier. This is now the C#9 and above rule applies. If I would remove that, now it compiles. But if I have no implementation, I could actually call this. So we could say, let's do it up here. We could say var instance equals new my class and call instance dot method, my method. But since there is no implementation, because it's yes, I can't call it here because per default it is private, so I can't call it. Actually, I need to call it within the partial class. Let's make a method here, public void my method. No, my other method, which now calls into this partial method. So we just call the method. So this compiles, but since there is no implementation, this basically gets stripped out, it gets removed because there is no implementation to this partial method. Let's put this into SharpLab. If I paste it in here, we now see that there is no, actually call this, let's call this partial method. Partial method. And this is my defined method, non-partial method. So what remains is the non-partial method, but there is no partial method. It doesn't get called because it has no implementation. Now I can supply an implementation. Let's define a second part to this partial class and actually supply an implementation. And let's console.writeLine. Now it works. And we see now that we have supplied an implementation to this partial method. Now it is there. Now we have the partial method, and in the non-partial method it actually does get invoked. So this is how it worked pre C#9, or also post C#9 if we do not explicitly specify the visibility, which means it is implicitly private, but doesn't necessarily have an implementation. If I would change it to int, it wouldn't work. It says no, it can't be. If I would have a out parameter, out string text, wouldn't work because those are the rules. But if I now explicitly state the visibility, I can still make it private. Now we need to have an implementation. And now also out would be, let's see, I apply an out text here. Now let's consume it, out string result. So this now works. But as soon as I have a C#9 style explicit accessibility declared at a partial method, it must have an implementation. Now, it doesn't necessarily need to be my user code that supplies this implementation, but a generator which supplies this implementation. So this is how generators make use of this new C#9 partial feature. I'm glad that, Deflux, I'm glad I could explain this. Actually, thank you very much for this question. I should have led with this. So great. So this is now the power of source generators and partial methods combined, and we could have the module initializer attribute, which when a generator needs some resources, perhaps a lookup dictionary defined, which has some resources initialized. This could be done in a module initializer. Okay, we checked out 2 generators which exist in .NET 6. There is more. I think there is a Razor generator, so the C# code when we write in Razor syntax, when we write .razor files, then the actual C# code then is generated by a generator. Currently, is the .NET 7 preview out already? I think it is, and I'm also not sure, but it may already include a new generator. So in .NET 7, most likely, currently in preview, a regex generator will be supplied. There is actually a video. I will then later on put this into the discussion. Let me briefly find this video. It's by Nick Jobsas. .NET 7 regex. There it is. Oops, I didn't mean to show.
Hi, my name is Bruni.
Hello everybody, I'm Nick and
Yes, and I will link this video then. So this is where he shows how we can save a lot of initialization cost via the source generator. So this would be a classic compiled regex, and this is now a source generated regex, which so the is match, or the matching is still pretty much performance wise pretty much the same between a compiled regex and the source generated regex, but the initialization cost is incredibly faster. I will link this video later on. So we can expect more source generators to come with .NET 7. So the source generators are going to be, if they aren't already, they're going to be a thing. Okay, cool. I briefly want to mention how we can test source generators when we want to write our own. This is the same set of packages that we used in the last 2 streams as well, when we wanted to test analyzers, code fixes, and diagnostic suppressors. So there is also a Microsoft Code Analysis C#.source generators testing package. Exists for MS Test, NUnit, and XUnit, and we can use this package to very similar. Then we can test analyzers and code fixes and diagnostic suppressors. We can test source generators as well, and we're gonna make very much use of those tests because we're gonna change later on old generators to new generators. So why I'm always keep mentioning those different versions of generators. Let's have a look at the implementation of a 3.8 source generator. I want to show examples that I've built previously. The first generator I built was actually, let's show it first what it does. So let's go to the example project. The first generator I have is basically something similar to name of. So what I wanted to have is, basically what you can do is with C#, you can say name of, and then let's say list. But if I say list of t, let's make a list of int, and white line this to the console. I will just return here. Let's ignore the rest. I hope that the output works now. Yes, so it will put out the name of the type, list, but not the generic name. So what I wanted to have to actually also put out the generic name. So I wrote a generator, which can now Let me inline this, which can, where we say white line. Now I call this type the friendly type. We can say name of, and then put in this generic list of t into the generic argument. And let's see if we run this application. We now see that the second one is the list of int. We could also do rather than name of, full name of, which now includes entire namespace. So we have the system collection generic dot list of int. However, the implementation it's not constant, because the name of this is actually, since this is a C# feature, this is const. So we can say const text equals name of the string, of course. But this doesn't work with the generator I wrote, because that's not constant, that's dynamic. There is still, it's not a const expression, because the implementation actually, well, it doesn't construct the string every time anew. Because previously when I wanted to put out, I have this code in some project, when I wanted to put out the name of the type in C# style, because actually, let's show the initial problem that I had. If I have string text and do type of the list of int, and then say get name dot, or is it toString, and put that to the console. Let's for now comment those two out and run it. Now we get the type representation, which is system collections generic list backtick 1. This backtick 1 indicates that this type has one generic type argument. Type parameter, sorry, has one generic type parameter, and it was what's the correct term? I'm not sure. It was defined with the attribute system.int32. And what I wanted to have is, rather than this backtick, sorry. What I wanted to have is, rather than the backtick 1, I wanted to have the C#. I wanted to have a C# style representation, not a metadata kind of representation with the generic angle brackets, and then not have system.int32, but if it's a language type, it's a predefined language type, then I wanted to have the language type actually. And what I did previously is actually do this with reflection. So at reflection, have a look, is this a generic type? If it is a generic type, get the number of generic type arguments, put in the opening bracket before, ending it there. Of course, trying to do this with a string builder to be more efficient, to be as efficient as possible, but it allocates a lot. And with that, I can basically with a source generator, I can basically inspect the code, understand this is a list of int, and then construct the string representation of this at compile time, and then reuse that very string. So if we have a look at the about what the generator generates, it's actually, this is how I solved it. There is most likely a more efficient solution. This is what I did to come up with that. So the generator creates two public methods, which basically reach into a dictionary. I have two dictionaries, one for the name of and one for the full name of. And then this dictionary gets initialized. The source generator understands all the usages of these methods, can already initialize this dictionary with the amount of usages. And then we basically map the type. What's always good practice is that the generator uses the global namespace identifier. so that our source generated code doesn't get confused with already existing user code. So if the user would write their own custom dictionary, which may be different because it may not have 2 type parameters, but generic type parameters, but maybe 3, then it wouldn't work. So this is why we always want to refer to the global namespace, that we indeed get the type that we intend, independent of whether the user code defines similarly, or actually, defines the type in the same namespace with the same name again. And we may run into ambiguous name issues. And then actually have this very string here. So this is not constant. I still need to reach into this dictionary, but it's significantly faster than doing it with reflection. I believe I used to have a benchmark here. But the benchmark would show that compared to a previously naive reflection kind of solution, that a source generated solution is both significantly faster and also allocates less, so puts less pressure on the garbage collector, which is good. So how does this generator now look like? Let's have a look at the implementation of this generator. So what's the anatomy of a generator? I have here this file. I called it, oops, that's the wrong one, sorry. The friendly name generator. And each generator has 2 things. It inherits of iSource generator, and it defines this attribute, the generator attribute, so that the compiler knows that this type is indeed a generator, so it finds it and then feeds in the past source code into it and expects it to potentially, source generator doesn't have to, but it may add new sources and feed them then back to the compilation. Let's have a look at this interface. So there is 2 methods. There is the initialize method and the execute method. So a source generator is split up into 2 parts. We initialize it and then actually execute it. So the execute step now would be generating code, potentially generating code. And what we can do in the initialize, we don't necessarily need to have the initialize. The initialize gets in a generator initialization context, just like with pretty much every Roslyn plugin that we write, maybe an analyzer or a generator in this case, gets in some context. And contexts now hold all the information that we have available. Like we always have a cancellation token. And we have here 1 method. We have the register for syntax notifications method. With that, we can create our own syntax receiver. I come to that in a bit. So this is optional. Basically, we could also have this empty, and it still could be a source generator. This is an optional step. And now in the execute step, somewhere we get now different context in the generator execution context, and eventually we call context add source. And there again is the name add source. We only add new code to the compilation. We cannot modify existing code in any way. So in chat there is a message to also that we need to manage those hard-coded strings. Not sure if you're referring to the hard-coded strings generated by the generator, or if we would manually create a string like a generic string. If you could clarify that, please. So this is then here we have actually source text. This is some C# string that then gets spit out to the compilation. Let's have a look at this receiver. What does a receiver look like? So receiver is a type which implements iSyntax receiver. And the iSyntax receiver has one method, onVisitSyntaxNode. And in this method, we get each and every syntax node of a compilation. What's a syntax node? Let's again go to SharpLab. If we have a look at, I've deleted the previous code, but let's have again a public record class myRecord, my reference record, int number, string text. If we have a look at the syntax tree, so this is now the Roslyn representation of this C# text, we see all the nodes that this tree is made of. So we have a using directive that is here. We have our method declaration. This entire thing is the method declaration. It consists of the public keyword, a record keyword. Then it has, this is now, we had a look at this at the first stream. No, at the first stream, yes, where we built an analyzer which for C#10 then warns if we do not explicitly declare whether it's a class or a struct. So we, since C#10, we have the class or struct keyword, which could also be none. We have the identifier, which is actually how I called it, and a parameter list, int number, string text. We can have a look at these. So there is 2 parameters. And those parameters, now one is a predefined type, which is the int, the integer, and one now has an identifier name. Because I used the uppercase string, if I go to the lowercase string, then again, it changed to the predefined type. Because the lowercase string, that's a well-known C# name. The uppercase string, if I do it like this, that's now from system.string, because we include system here. But we could have technically our own string. I could have public. I could have myself a namespace. I shouldn't do that because this will cause issues, but I could have my own namespace system and define my very own public class string in here. And now we actually get a warning because it conflicts. If I remove can I remove it? I can't remove the system. Yeah, yes, I should be able to remove the system here actually. They're using system. And no, okay. So yeah, it actually conflicts. But what I could do, let's define my own namespace. I call it system2. And now refer here to system2.string. And this is not now the system string. This is now it could be my string. And we see all of these nodes. All of these nodes now get passed in to this syntax receiver. And what we can do now in the syntax receiver is see, am I interested in this node? Because what I want to do, if the user would write something like public, let's say in their class actually, boop. If the user would write friendly, come on, friendly dot full name, passes in int, and have a look at the syntax tree. I want to find all full name invocations which are on the type friendly. And then they are subject, then I may be interested in them and generate source for that. And then analyze this type parameter and add then an entry to this dictionary. So this is basically now what we do in the generator. We find all the invocation expressions. So when we invoke either method or property, we know that the expression, no, we don't know, but if this expression of this invocation expression is a member access expression, so if we access a member, then this is more interesting. So basically what we filter here everything which the generator is interested in. Then we expect this to be a generic name because we have generic type parameters passed in. So we can get this type argument list. And I know that this method that I defined only has one argument. So I can filter for only one argument. If it has two, this is not the type I intended, so there's nothing we need to generate for. And the argument list itself of the method itself doesn't receive an argument. So this can be 0. And then we have two if blocks here where we basically determine, is this either the name of method name or is it the full name of method name? And then add it to two collections, so either one of these collections. And so this is now how I can find out all the potential invocations of the method that I want to create source for. So I'm reading through the chat. Would there be any point in inheriting system2 string from system string? I think system string is sealed. Actually, I do have a string here. I believe it's sealed. We can't inherit from string. Yeah, so it's sealed. What we also see that the system string, it's actually partial. So the .NET team also, string is a big type. They have moved the implementation of the string onto several files. Actually, we see it here. So, for example, they moved all the comparisons. Oops, let's have to off this. If we would jump to the GitHub repo, we would see basically the very same thing. So they have a partial class in the comparison.cs file, string manipulation, string searching. So they basically grouped functionality into separate files of this one big partial class. If they do, yeah, so we can't inherit from system string. The if statement, yes, the if statement. So with syntax receivers, this can be. I found to use the property matching for me the nicest way how I can read this. You could also have it just with if else's if you prefer, but I'm a bit of a sucker to use the latest C# features. So this is C# pattern matching. Yes, that's Tyndall. That's quite an if. And yeah, so now the syntax receiver adds those types. It basically extracts. If I jump to the example, it basically extracts. We have here several usages of name of. It basically extracts. Oops. This type here. So this type information that we pass in to this name of method. So we want to know that so that we then can, for each of these types, if we jump into the source implementation, for example, for each of these types now, actually let's show them side by side. If I move it down here, we see that the name of dictionary of int bool dot enumerator now generates here the type again and generates the string. So we need to extract this type information. And this is what the syntax receiver does. And then in the execute method, since the syntax receiver is optional, we don't necessarily need to have a syntax receiver. I now need to check if the syntax receiver actually exists. So I have a debug assert here. The syntax receiver is not null. If I have a look at this, hover it, we see that this is nullable because it's optional to have a syntax receiver in place. And we check, hey, is it actually, if I say is friendly name receiver, I actually do 3 things. I first check if this is not null. I check if this is actually this implementation type, and then assign that to this receiver local variable. And then I have more methods. I have the get distinct. Where's my cursor? There's my cursor. I have the distinct name of invocation. Now, this distinct is very important because the user code could, let's jump to an example again. The user could, for example, I perhaps do a little simpler example, have this method invoked with the same type twice. Now, I have this invocation, the syntax tree twice with the same type, but I do not want to generate in this dictionary, I do not want to add the same generic type twice, because then I would get an key already exists exception. So I need to get the distinct versions of it. So this is basically what this method does. So I pass in the name of invocations, also pass in the compilation. I would just have a brief look in it. It's not necessarily source generator things, but Roslyn things. So we have some code in here where we can now determine all the distinct invocations. So this is, I tend to use a hash set for that. We pass in a symbol equality comparer, and basically then find the type information. And if it is a tuple type, then we get the underlying type of this tuple. And so we basically filter now. We filter out duplicates. And then we go into the generate source method. And now comes the string part. We see there's a lot of strings. There's a C# string. There's a C# string. There's a C# string. So what we add to this compilation is a C# string. How we create this C# string, maybe we do it with, for example, what I do is with we are an idented string writer, because we can, like here, increase the indentation and decrease it again, because I like to have the source generated text formatted nicely, so I can nicely inspect it, but it doesn't have to be. So you'd use any mean how you would create a string which happens to be in C#. So I get the language version, because it was also interesting to keep in mind to keep the language version in mind. The source generator, that's now a compatibility question. If the source generator would generate, let's say, C#10 syntax, now this generator wouldn't work for any project which doesn't have C#10 enabled. If they use C#9, but already use a C#10 feature, then the generated code would cause a compiler error. Not the generator itself, but the code that the generator generates would cause a compiler error. This is not the best usage. So we should keep in mind to perhaps either produce lower language version, or what I do here is actually then find out which language version this is. So this is basically just properties where I say, hey, is this C# language version 2 or higher? Or is it C# version 9 or higher? So I try to find out which features are supported and then use these features. So this is one way. You don't have to like really generate different features. Maybe it's fine to generate a C# 7.3 compatible string, for example, because C# 7.3 is the default language of Net Standard 2.0, and a lot of packages, I guess, use C# 2 or above or compatible. So this is one way to approach it, but always keep compatibility of the code that you generate in mind. And yeah, so basically what we do then is to find out find out what languages are supported, and then actually generate the code. So we see public static string, this is all code that is generated, and eventually then ends up, if I jump back to the example, generating this very text file. If I remove all the user code, the generator at least produces one thing. If I remove everything, and I jump to this file, it still generates that. Do I need to recompile? Sometimes it doesn't pick up the changes immediately. Then I like to go, I'm sorry, I closed the command line again. Then I like to, on this side, do a .NET build --no incremental to force a rebuild. And now I was expecting this file to change. Not sure what I'm doing wrong. Perhaps this is a good use case to show another feature, because I said, well, the source generator doesn't add sources as a file. But what you can do is in MS Build, set emit compiler generated files to true, and then with compiler generated files output path, tell the compiler where it should actually physically create those files. So we could now go to this file location. Let's jump to the file system view. We defined the base intermediate output path. This is the object, the obj directory. So let's jump to them. And there we now have the generated folder, which is this one. And here we now have, for each generator that we have, so I have multiple generators in this project, we have one folder. There is my friendly name, and here is the generated file. Okay, this is what I wanted to show. So if I have no usage of this class, so this is the basic stub that the generator creates, in order to enable IntelliSense, so that I can, and auto-completion. So I defined this in the f0.generated namespace, in the friendly class, and then we have empty, name of, and full name of methods, which just throw some exception. By the way, this exception is also source generated. So this should never happen, because if the user now happens to call f0.generated.friendly.nameof, and let's invoke it with int, save it, I will build again. So this is a bit of an issue that both Rider and also Visual Studio have. It doesn't always pick up the latest generated source and displays it in the editor nicely. So sometimes this is how I work around with it, to have a command line in place on the side and do a .NET build, no incremental, to kind of force it. And now we see the dictionary has been added, and we no longer throw the exception, but actually search into this dictionary to receive type of int. Now indeed, return the int. And let's also showcase if I lower, because I made this generator language version aware. If I jump into this example project, oops, I hit F5. I wanted to hit F4. So if I now jump into the CS project, we have it below. If I set here we set the language version to 10. Now let's set it to C#7. Well, let's go crazy. Let's set it to C#2. So how does the generated code look like? I will do a rebuild. If we set it to C# version 2. Now this should change in just a second. But it doesn't. Did it? Oh, no, I have a compiler error. Okay, I use another feature. I use nullable. Yeah, so let's use at least C#8. Or let's disable nullable. Let's do that. And disable implicit usings because they're not supported on C#10 either. Yes, so this now should compile. No. File scope, so because I actually use file scope namespaces. So let's convert that into a scoped into a block scoped namespace. Did I fix all compiler errors? No. We also have using static. Excuse me. I have this in. I have global usings. Where are they? There they are. Of course, I need to remove the global usings here. This is not supported in C#9 or below. Now let's add the using system.console. Actually, don't need it here. Okay. Did I fix all the compiler errors now? Yes, I have. Okay, cool. And now the generator, now we see the generator generates different text now. Let's bring this in big. Now it generates C#2 compatible code where we don't have an object initializer, for example. So I need to first initialize the dictionary and then add to them one by one. What we have previously is a collection initializer. What we also don't have is name of. So yeah, I create a string here like so. And yeah, so this is one generator. Another generator I wanted to show is an enum info generator. One thing about enum.toString is, let's jump into, let's do, which projects do I consume here? None so far. Enum, what enum comes in mind? String comparison. The string comparison enum. So that's the enum. String comparison equals string comparison.ordinal. Oops. And we can toString this. So let's do system.console.writeline. And we can say .toString. And this indeed puts out the name ordinal in here. However, enum.toString is not the most performant thing. There is a talk I will, if I haven't linked it up in the discussion already, I will do this afterwards, by David Fowler. It's called Implementation Details Matter. And there he shows that how this enum, he uses a log level here, the toString is implemented. It actually internally does so it gets those constants, caches them, and then does a binary search on them. And what a faster, more naive implementation would be is to basically have a switch statement where we now for each enum define the string constantly. And this now not only allocates nothing, but also is faster than the binary lookup. And this is perfect code for a source generator because we know the enum, we know which possibilities, which constants this enum have, and what name it should spit out. Now, if this would be a flags, this would be more difficult. I tried this as well, but then aborted this, so this only works for non-flags enums. And our generator could now, I called it enum. So there is also enum.toString A different approach to get the name would be enum.getName, where we can pass in, this enum here. So this as well now puts out to the console ordinal, but the implementation of enum.getName, I believe, is very similar. It's not executing the exact same code, but it also isn't super fast, and it also allocates a little bit. So what I did is then write my own type, the enum info type, which also has a get name, and this is now source generated code. And if I run this, this produces the very same example, the very same ordinal string, but this is now generated from a generator. So if I hop into the code, we see exactly those. We have some compiler errors, but nevertheless, see what was suggested by David Fowler to basically have just a naive switch on those. Actually, I should. Oops, sorry. Let's recompile. Does this update then? This is again an issue from the IDE. Visual Studio has the same issue. It shows me previously generated code that was generated when I started the solution. So let's again jump to the file system view and go to the enum info generator and see this output file that we did via MS Build. There it is. Okay, now we have it. So this is now what the generator generates. We have the switch, and for each constant of this enum have the string. And if I would now go back to the CS-Proj and enable a higher language version, let's go back to C#10 and let's build again. Now we will see that the code looks different because we now have the newer C# switch expression. And so it's not, so what we had previously is the switch statement. This is now the newer switch expression. And we can also make use of the name of keyword. Not sure, was this introduced in C#6? Not entirely sure. But again, this generator is language aware, and depending on the language that the consuming project has, creates different implementation. And yeah, so this is again where source generators shine. They can produce code for otherwise tedious implementations. We could totally do this ourselves, but we already know what we're gonna do, so we could have basically, have it automated. And this more naive code is now more performant as well. So let's briefly have a look at this generator as well. And we will see it's quite similar than the other generator. Again, we have our iSource generator with the generator attribute on top. What I didn't show you before is actually here I defined a hint name that eventually in the add source down there, we also can pass in a hint name. So this is now a hint to the tooling to basically say, okay, although this file doesn't really exist, to tell the tooling, okay, this is how the file could look like. And then with this MS Build flag enabled, then actually produces this file like so on the file system. And again, in the initialize, we register ourselves a syntax receiver. Let's have a look at the syntax receiver. Now the syntax receiver, again, this now looks for get name invocations of the type enum info. So we find all the invocation expressions we expect in the argument list. We expect one argument, and the expression, the identifier of the expression, we expect to have this enum, this method name. This is, does it show? Yes, it shows. Oops. So this is the get name method. So we expect get name methods to be invoked with one argument. And now they aren't necessarily the methods we are looking for, but those are the methods, those are candidates, what we can analyze from just with the syntax tree, from the syntax node that we get passed in. And if it is, we now have a method, the getArgument expression. This basically now gets the expression. So this expression now yields the type of the enum that we passed, and we add this into a list. That's then all of those candidates now the generator could use now to create source for. So again, we check, do we have a syntax receiver? And if we do, we go into this method where we now get the names. Here we get now the names of the types. So we actually, because the input is a syntax node, but we need semantic information. We need type information. So we basically extract named type symbol, which could be, for example, in our case, the string comparison type. And with that string comparison, we put this into a hash set. Again, a hash set to avoid duplicates, because I don't want to create, well, if I would create the method for the same enum twice, we would have the same method with the same arguments, with the same parameters defined twice, and this would cause a compilation error. So we only need to do it once. And yeah, then we extract the information here. Then as a next step, we also get options, because source generators also can be configured. I'll be showing this in just a second. The implementation is not so important, because this is actually similar than with analyzers. And analyzers can also get options, such as reading it from an editor config, or from a global config, or from MS build, also from the CS-proj MS build properties. And then we have a method that generates a source code. Again, we have our string writer, where it's always good practice to always add an auto-generated comment on top of each file, because so that other analyzers know, okay, this is auto-generated code. I don't want to analyze it. I don't want to produce warnings for that generated code. So always put the auto-generated comment on top. And then again, we see, okay, which does this feature have? Does this project have nullable reference types? So is it at least C#8 or higher? Then we we enable nullable reference types, and create a namespace, create a class, and so on and so forth. And then depending on the features we have, we now generate somewhere this switch expression. Okay, here there's exceptions if something isn't found, and we trained the method, and for each enum type that we have. So the implementation isn't that important, but basically what we do here, we assemble our string that we then want to put into the compilation. I mentioned options because for this very generator, I also introduced some options. So we could, where do I have it? I believe I have it here. Okay, let's again jump into the file system view and go to, do I have it here? I have it actually here. Go to the obj file. Oh, I don't have this enabled here. Let me quickly enable it. So I go to the sample project, copy this MS build, those two properties, so that we can output the files to disk, so that we can view them, how they're really generated. Go back to this project, edit here. Now let's build and see. Here we are. Yes, no. Did I add it to the wrong one? I meant to edit here. I did. CS-proj. There I added it. Okay. Obj. I should see now the generated sources. There they are. Okay, excellent. And let's open this file. And so what I do have in place here in this project, we have a global config. And in this global config, I defined the f0 gen underscore enum throw. So this is basically a configuration that we can set. If I set this to true, then the implementation of this enum info get name. Let's have a look at this method. Oops. Let's have a look at this method. So the implementation here now, if this member isn't found, or if this constant isn't found, because what the user could do is don't pass in an enum by the type name, but basically since an enum is like an integer, so what we could do is, let's jump to the example. What we could do is actually pass in here 1 and cast this to this string comparison enum. So this is fine because 1 exists. Enums are basically integers, so per default, if we could also change it to a long or some other integral type, but by default every enum is an integer. And so the first constant is 0, the second one is 1, the third one is 2, and so on. Oops, and so on and so forth. So we have values until 5. Now if I would pass in 6, there is no constant associated with 6. It's still a valid integer, but there is no constant representation of 6 in this enum. So now this method could either fail, throwing an exception, or return null. And this is what I control with this flag. So if I have it enabled, we actually throw if it's not false. So in the default case of this switch expression, we throw an invalid enum argument expression. But if we happen to disable this, I set it to false, build. Now we will soon see it switch. I was expecting it. Oh, I have warning, but this shouldn't hurt me. Now I expected this to actually show that it now returns null. Let me briefly find out what I'm doing wrong. Am I the wrong project? Should be in the correct project, yes. Info. Do I have something else set? False. I'm not entirely sure what I'm doing wrong, I'm afraid. Okay, but if it would work, I have some issues with the tooling. Not sure what entirely is wrong, but I do have tests for that, so this works. Perhaps I can show it. I will come back to this later if we have some time. But now it should generate, if it is the default, it actually should return null. And then this entire string that we return becomes nullable. Nullable if we have C#8. If it would be on C#7, then we don't have nullable enabled, so we can't create this nullable string. And so this is how we could read configuration, either from an editor config, or we could also place it in dflux. Thanks for following. We could place it in MS build. Okay, but I will circle back to that later on. What I wanted to show is that we can also have those are like analyzer config options. We could have a look at this as well. And what we also could have is additional files, which are not C# files. Our generator, I don't have an example for this here, but what we could have, if we jump to the generator execution context, we also have, so this is all the properties we have. We have the compilation. We have the parse options. So those are the C# parse options with which we can determine whether this is C#7 or C#8. With the compilation, we find out what this type that we have in the syntax node actually is. We could have here our analyzer config options. And we could also have additional files. In a compilation, we can mark, for example, a text file or a JSON file as additional file. This needs to be explicitly marked in MS Build, and then the generator could also inspect these. So we could have a generator, technically, which gets in a text file, which is in some... There is one example where I think either an XML string or a JSON string is then actually passed into, or generated into C# types. And yeah, so this could be any file. So this is how generators are written. If we want to now publish this generator in a NuGet package, for example, there is also some things to pay attention to. One thing is source generators are net standard 2.0. This is how it works because they should still also work for .NET Framework. For example, Visual Studio is based on .NET Framework, so for backwards compatibility reasons, just like an analyzer, source generators are .NET Standard 2.0 because generators are technically analyzers. What I do here, I multi-target here for 6.0 because I want to have the 6.0 nullable annotations so that the code that I write, the source generator code that I write, is null-aware. Then we want to set some NuGet flags. So we make this packable. We do not want to include the build output because why don't we want that? Not entirely sure, but we don't want that. I said here explicitly, I never want to suppress any. So we want to suppress the dependencies. So this is only the package itself, not some other dependencies coming in. And this is one important part, is to set the development dependency to true, so that a consumer which consumes the package automatically gets basically this, the private assets all. What I described earlier, we don't want analyzers in general or generators in specific to sensitively flow to consuming projects. And yeah, then we set some NuGet properties. And then for debugging purposes, we could set the is Roslyn component true. This is something that Visual Studio does. And we have, this is basically it. But since we now have not Net Standard 6.0 and Net Standard 2.0, we need to tell when packing which target it should take. And we can do this via here. So we only packing the Net Standard 2.0 target. And let's see how our generator actually looks like in the wild. Let's go to nuget.org. Let's go to this F0 generators project and jump to the NuGet package explorer. And what we see now is very, very similar. It's the same as any other analyzer. So we have in this package, we have no lib folder, but we have an analyzer folder. And here is now our analyzer package, our analyzer dependency. And we see, if I go to the dependencies tab, there's no dependency. The implicit dependency is, since this is a source generator, and we have built this source generator with, where is the package? There it is. So this is the important package. This one. Oops. The Microsoft code analysis C# workspaces. We use version 3.8. And version 3.8 basically means .NET 5.0 SDK. This is important. So if I have a .NET Core 3.1 SDK or in .NET Framework, this wouldn't work. This requires at least .NET 5.0. And before we do a little break, let's have a look at what has been added in So this is we now inspected 3.8 source generators. So what does a 3.9 source generator? There has been one addition. So 3.9 generators now have one additional method. So in the initialize method, we can say register for post initialization. And this is basically, this could generate code unconditionally. So the only thing we can do is we have this post initialization where we basically then can add source. But in this context, we don't have any node available, or we don't have any compilation. We have nothing. We have a cancellation token and the add source method. That's it. We don't know anything about the compilation of the user code yet. So we could emit code here that is unconditionally added. We always add it. Now, one use case would be, because another limitation is that I forgot to mention, source generators cannot depend on each other. In this project that I showed, I have 3 different source generators: the friendly name generator, the enum info generator, and the generator which creates an exception. They don't know of each other. So one generator cannot depend on the output that another generator produces. However, generators can depend on output that we register with the post initialization. So in the later step, in the execute step, we can ensure, I have this in this example here. So I create in the post initialization, I create this Roslyn 3_9 type. And later on, we can actually in the execute from the compilation get this type. So it is available. But again, so post initialization steps cannot depend on each other, but the regular execute step may depend on any other post initialization context. So this is how somewhat generators can depend on each other, but in general, they can't, and they can only add sources. And now with that model, there is one big issue, and it's the syntax receiver. Because if I jump back to the generator project and have a look at, for example, this enum info generator, and now get into the syntax receiver, we learned that this receiver gets called for every node. If we include this generator in a big project, let's say the .NET Runtime project, there's a lot of nodes in there, and the editing experience would get bad, because for every key press, I hope I can show this example actually. If I run, do I have it here? Let's show if I can show this example. Let's actually, why do I run? I don't need to run this. What I want to show is the output. Let's again go to the file system view. Let's have a look. There it is. We have a generator here. Yes, let's have a look at this 3.9 generator. Do I have it here? Yes, I have it here. So I have a generator which basically generates or adds the amount of nodes visited. And what I want to show if that is that this happens every key press. I hope this example works now. If I press a key. So it doesn't. I recently switched from Visual Studio to Rider. I have something wrong with my setup here, I'm afraid. But what I wanted to show is that for every key press that we type, we now pass in to that syntax receiver each and every node again. So every key press feeds in the entire syntax tree of everything again and again and again. And if we have a huge project and this takes, for example, 1 second, I need to wait 1 second after each key press, because potentially the IDE is busy running the source generators. And this wouldn't be a very good editing experience. And this inherited problem of this syntax receiver setup now leads to .NET 6 and the Roslyn 4.0 incremental generators. And how they fix this problem, we will have a look then live in a bit, where we will actually, those generators that we had a look at, we will live convert them into incremental generators. And they don't suffer from this syntax node problem anymore. And how and why, we will come back to after a brief break. Welcome back. Thanks for sticking around, or perhaps jumping to this position, depending on whether it's now or later now. I will put the recordings onto YouTube, I guess in 2 weeks, something. So if you want to review anything or now watching it live, thank you very much for joining in brackets again. So we now had a look at how generators, what they do, how they work, and why now recently in Roslyn, recently in Roslyn 4.0, which is .NET 6 SDK and above, incremental generators have been added. If you want to dive into the incremental generators, what they do in detail, I linked in the resources a talk by Chris Sienkiewicz. I hope I don't embarrass myself with pronouncing his name, where he goes into detail again about the issues of the syntax receiver approach and how the incremental generators work. And they work, so the clue is they work incrementally. Let's have a look at a generator that we saw previously. I'm now in the .NET Runtime repo. Let's go to logging.abstractions. We have a gen folder here. This is where the generators live, or the source to the generator lives. Let's jump to the generator, and now we see we have the incremental generator. That's a new one. And the big difference is what they do is they basically build up a pipeline. So they don't analyze each and every node every time again for each compilation, but do this incrementally. So we have several steps in the pipeline, and if an earlier step in the pipeline changes, then the later steps have to be executed again. But if this earlier step doesn't change, the later steps in the pipeline don't need to be executed again, but can reuse a previously cached result. So, for example, if I have 7 files in my compilation and I only edit 1 file, now the syntax tree of that file needs to be put into the analyzer again, but not the other syntax trees because they haven't changed. Now this is only partially true, but something like this is the model. And so that we don't need to do everything again, but can reduce it to the scope of what has changed since the previous step. And this reduces now overall complexity and improves the editing experience. Which basically means that if we do a .NET build, then each and every time everything is analyzed. So every node is inspected. This is how it works. But if we are in an editor, now that the tooling could be aware of that and make use of the incremental generator and improve the editing experience by only modify what has been changed or reanalyze for what has been changed. And this model is now a little bit different. We have no syntax receiver here. We only have the initialize method, and we build our pipeline. So the context has several providers. For example, the syntax provider. The syntax provider is basically the replacement for the syntax receiver. And we build our syntax provider. And then after this step, we add another one. So we also need the compilation for this logger message generator. And we get that via the compilation provider and combine that with the previous step. And this could be multiple steps. And basically, this is how we build our pipeline. And eventually then, we don't add the sources directly here, but we only register a callback which then actually outputs the files. And perhaps let's have a look at this, how this is achieved by changing our existing 3.8 generators to now the Roslyn 4.0 incremental generators. I also want to shout out this GitHub issue where I asked how this is working. I thought it wasn't working. So it was working with the context, with the system, with the Microsoft.codeanalysis.testing packages. I thought that testing incremental generators wasn't possible, but it actually is possible already. I used it for source generators, but I applied a way too complicated approach. It's super simple to switch to use the incremental generators. I will open those two files as reference for me now to do everything right. So we basically need to change this to incremental and here as well. And this should basically it. Okay. Then let's get coding. Yes. I will briefly have a look in my changes list. Actually, yeah, I'm doing this here. Let's get rid of some changes that we this one we need that we made previously. All right, okay, cool. So we have a clean state to start. Now let's start with the least complex generator, the source generation, this generator which generates the exception that I use for the other generators. So the first step is to change the I source generator to I incremental generator. But we see this type isn't available because I'm still targeting, where are we here? Code analysis C# workspaces 3.8. So this is still the .NET 5 compatible analyzers, and incremental generators have been introduced in version 4.0. That is actually 4.0.1. So we want to upgrade to that. And basically, I now introduced a breaking change. So this generator does not work with .NET 5.0 SDK anymore. It only works with .NET 6 SDK and above. But I'm fine with that because I think in May, the support for .NET 5, since this is not an a LTS, is expiring. So I will be. It's for me. It's fine to upgrade. But that of course then depends on your generator that you have and where you consume it. It's, I guess, if you use it internally, it's more likely that you can upgrade without breaking anyone. And now we have the incremental generator. Cool. We still need the generator attribute. So we basically only change the interface and implement the missing members. I will put this to the top. Let's put it here. And we now need to get rid of this method. This was an old one. I had 3.8 as a comment and here as well. So we need to replace those with the new logic. Let's do this to a statement body. Okay, so first we don't use a syntax receiver anymore. What we do now have is a syntax provider. Actually, let's first see, let's keep the throw if the tests are running. Because this is what I had issues with previously. Okay, here they are. Unit tests, let's see. Let's cover them as well, so we can enable continuous testing. And I have, oh yeah, build errors. Okay. Okay, I also need to upgrade the testing package, of course, to use, let me copy this dependency also to the testing project. Okay. Does it compile now? Still not. We have, okay, those projects they have issues. I will exclude the example projects for now. Only have the source and the tests enabled. Okay. And in the tests, we need now to upgrade to use So this is now the actual test of this generator, and here we have a compile error because, okay, we have now changed this to an incremental generator, but this is not compatible with the previous one. So this is what we saw from the GitHub post. I need to update this to incremental generator. And since this is a partial file, there is a second part to it. Put it here as well. Great. And here, and this is the step that I did wrong previously. Let me refer to this example here again. Yeah, I need to use the empty source generator provider. I guess internally then, what this does is mapping this incremental generator. Although this is really, really empty. Okay, this is, I guess, just to satisfy the interface or the API. I think internally then this incremental generator is mapped to a regular generator. Actually, I'm not entirely sure, but this is how it should work now. So let's rebuild. Why are these failing? Okay, now the other tests are failing as well in compiling because I now dropped compatibility to the non-incremental generator, so I will now update every. I have 3 generators, I update all of them to incremental generators. Let's implement the method, but put it to the top, but let it throw for now. Okay. Now put them here. Okay, this should get rid of most compiler errors at least. Yes, excellent. Now we have some warnings because we have unused methods. And let's fire the tests. Cover selected unit tests. Because I want to enable continuous testing. Yes, please. Oh, yeah, okay. And do I have the mode set to save? Yeah, save is fine. Okay, now the tests are failing because we don't, so this causes some issues, I assume because we throw. So let's get implementing. Let's jump to this original generator that we want to build, convert. So, okay, we don't have the source generation. Control, Shift, Escape. We don't have the syntax receiver anymore, so we can now use the syntax provider. And we use that to create a syntax provider. And the syntax provider here has, let's jump to it, 2 funcs. One, which is the predicate, where we get in, so this is very similar to the syntax receiver. We again get in every node here. So we can, and then we return a Boolean. So we can tell the pipeline, are we interested in this node? Yes or no. And the second function is a transform, where we can transform, change the type into something that we need. So we can have any T there. So let's have our syntax provider, I call it predicate, and our syntax provider transform methods set up. Let's create those methods, get rid of some windows here. Okay, create method, yes. And create that method, yes please. Put them in order. Okay, cool. And now we can basically, we want, I copied both methods now actually over to the other part of this partial file. No. To where the syntax receiver usually lived in. We will now get rid of the syntax receiver. This should also be part of this partial file now. So this is also part of the friendly name. No, I'm in the wrong type, I'm afraid. I meant to go to the syntax receiver. Yes. Remove the syntax receiver, make it part of the partial source generation exception generator. We can get rid of this. So what it did previously, it exposed a list of identifier names. So we now need to extract those identifier names differently. Okay, put in both methods here. And what we had previously, this if here from the syntax receiver, I just used this as the predicate description. So we have here our syntax, that's our syntax node. And the second part is the cancellation token. Okay, so we now have the, shouldn't have auto building. We can return that. So we now know if it is some identifier name syntax. So that's the first filter. And then we want to transform it. So previously we just added it. So basically we can now return that strong type. It was what was the type? I should have recorded that. Yeah, identifier name syntax. So we can have our transform method return the syntax identifier name. And we get in a context and also a cancellation token. And the context carries the node. So we can basically just return that. We know already, because we filtered up here, it is an identifier name syntax. So we can basically as identifier name syntax here. Okay, it's not the context. The context has the node. Now we get a nullable warning, I suppose. Okay, well, we could either ignore that. Yeah, let's suppress that because we are the null forgiving operator, because I know this is not null. Actually, we can also, just to be sure, at a debug.assert, say this node indeed is that identifier name syntax. But we filtered here before, this only returns true if it is, so that's fine. Okay, so now we basically I disable the build on save actually again. I'm used to saving all the time. So let's do it on build, yes. Cool. Now to the next step. What else do we need to replace? So we got rid of that. Let's see what we have next in store. Since we have no syntax receiver, we can just safely remove all the syntax receiver code. Oops, I meant to outdent. Yes. What else do we need? Okay, we need the pass options. So somehow we need to get the pass options. What else do we need? That's pretty much it. And okay, and here we get the references. So let's see. Let's store this. This is now our syntaxes. Syntaxes. Is the plural of syntaxes? And now we want to define the next step of the pipeline. So we need the pass options, and we can get them via, we don't have the pass options available, but we can basically put them into the pipeline. And we do that by getting a hold of the pass options via a pass options provider. Perhaps we should have a look at this incremental generator initialization context first. It doesn't have the compilation or the pass options directly or the additional texts, but it has provider to these. So there's a compilation provider, a pass options provider, an additional texts provider. And this is now those are all of this incremental value provider. So this incremental value provider is this core type which is used in building our pipelines, our generator pipelines. And we want to combine that step with the syntaxes that we got before. But this doesn't compile because I believe because the combine expects, incremental value provider. Yes, but the syntax provider actually creates an incremental values provider. Yes, so that's the difference. So this is an incremental values provider, but we need an incremental value provider. And we can basically condense that by doing collect. So let's do that step. I call this collected. Syntax is .collect. Oops. So this collect is now actually collecting basically getting all those node information out of the trees and invoking our callbacks, our predicates, and our transforms that we just registered. And now we have an incremental value provider, and this is no longer the index name type directly, but it's an immutable array of index name syntaxes. If you remember, in Roslyn, everything is immutable. And we can pass in those collected and not as compiled. So let's see what we get. I call this combined. And the explicit type is this. So we really get the combination of this. So we again get another incremental value provider, but this now holds the information of the pass options and also those name syntaxes that we filtered. So that's cool. So perhaps let's give them more descriptive names than left and right. Call them pass options and our syntaxes, or syntax nodes, perhaps. Okay, and now we got everything ready that we need. We can now register our output. We do that by via the context. We can now register our source output. I believe this gets 2 parameters. One is a callback and one is the source. Yeah, okay. So we pass in a incremental value provider, one basically those pipeline that we have built up and combined with, and pass in an action that we want to execute. So we pass in our most combined value provider, and we have then our source output action. Let's create this method. This method now gets in a source production context, and with the source production context we can add sources just as we had before, and we can also report diagnostics. I didn't mention this before, but also with the 3.8 generators we can report diagnostics just as an analyzer would. So for example, to indicate to the user, to the consumer of our package, that they're using our generator wrongly. Maybe they need to put an attribute somewhere, or need to make something partial. Maybe something is missing, or maybe something is invalid. And we could produce warnings already rather than later on failing during runtime because the code couldn't be generated. And we get in, okay, so we have here our context. And we get in, let's do a break here, those combined value providers that we have. So we have in our pass options and we have our syntax nodes. Let's call this our source. And now we should be able to replace this execute method. So I take the entire body of this execute method in here. Now we removed all the 3.8 code and basically need to refer to what we have built in our pipeline. So the context doesn't have the pass options because we only need the pass options if we combine this in our pipeline. And we can now say source.pass options. There we have them. And the rest, we leave the rest of our code how we actually generate the source code untouched. That still works. We generate the code, and actually in this analyzer, we do report a diagnostic as well. Let's see. So this diagnostic gets in the identifier name syntaxes as well. So we need to pass these. We can say source dot, that's the syntax nodes. Okay, but this is now an immutable array of, it actually compiles. Yeah, immutable array actually implements I-read-only collection. I may be changing this later on. And okay, the context is now a different one. We no longer have the generator execution context, but the source production context. Let's see what else do we need in here to generate. So this is some code where we eventually create an analyzer from. Actually, this diagnostic reports if we directly use this exception. So the source generator exception that I have generated here should only be, it should indicate that something is really, really bad, but the user should never refer to it in their code. This is not how I would like it to be used. So this is why I produce a warning. And so I need to pass in the context. So, but the context now has changed. There's a different context now. It's now a source production context. So I think I only need to change the type and we're good to go. It seems to compile. Let's see how our tests are doing. What is failing here? Did I change code here, which now? Why is this no longer working? Internal seed class. That's interesting. Convert expression from. So I removed syntax receiver here. From this type, I want to do this later on. Okay, great. Now it compiles. So let's see how the tests are doing. Are they failing actually? They are still failing. Okay, I believe I forgot something. Let's go back to the example that was put in the description and compare it with our setup code. So let's jump to our verifier here. Okay, we do have we have we don't have this. We need to get the source generator. Okay, this is the I see. This is the important step because we now have an incremental generator, but this doesn't work with the already existing tooling because the existing tooling expects a source generator. But there is a way to convert the incremental generator, this one, into a regular source generator, and then everything should be cool again. I hope. Let's see. What's the name of the method? It was get source generators. Okay, override get source generators. We get this and say as source generator. Is this an extension method that I'm liking? No. Okay. We don't just convert it, we create a new. I see. We actually pass in here an empty source generator, but we can't use that empty source generator because the empty source generator does nothing. So we need to, the type that we have, need to create a new one. Okay, so I will copy this code. We create a new T of source generator, which is our incremental, where is it? Our incremental generator. And then we convert this incremental generator from an incremental generator to a source generator. Okay, now I hope we have everything together, because this is the step I failed last time while testing source generators. Yes! Okay, before I forget, this works excellently. Thank you very much. Cool, and the tests are green. But let's do a small manual mutation test to see if they're really green. So I just jump somewhere and I change here something. Okay, I modified the text, hit Control Save, do the test execute. So I need to run the tests, and now at least one test down here should fail. And it does. Excellent. So we expected nullable enable, but it was actually nullable a enable. Cool. 60 or more modifications, so the tests still seem to work. So we now successfully converted one 3.8 source generator to a 4.0 incremental generator. Now let's do this for the other two as well. Which one is less complex? I believe this one. Let's have a look at this one. So this is the friendly name generator that's doing somewhat of a name of thing which supports generic. And let's do the same steps again. I'll go ahead, move this window, go ahead, and first we need to again remove the syntax receiver. So I will jump to the syntax receiver. We don't need that anymore. I want this to be also part. I define this the partial class. I want to do this to be part of the generator as well. Can get rid. It's okay. We now with this syntax receiver created actually two different collections. Syntax, the name of invocations and the full name of invocations of both those methods. I will keep this for now. Actually, I will comment these out for later reference. And this was our previous method, and we want to replace that. Okay, so again, the same step. We now define our own syntax provider, where we have our syntax. At this time, I just call it our predicate and transform. Okay, that's a bad name because that exists already. No, let's stick with syntax provider predicate and syntax provider transform. Create both methods. Actually, I can generate it right here. Okay. But I want to move it up here. Okay. Move both methods in this file of this partial type. Okay. And again, so we have here quite an if statement, but here we need more. So I will again take the entire if statement. So here return that. We have here our first argument is syntax node, second one is cancellation token. Okay. And we previously were interested in the name and in the arguments. So we now need to extract that in the transform method. So we have here our context and our cancellation token. So let's see how we can achieve this. I will check this out later on. I first need actually, let's do it right away. Let's put this code up here, because this code used to transform and add this to the collections that we had earlier. And we need to first need the arguments. So I type checked this thing. So this syntax node is an invocation expression. So we can assure that this is our expression. Context.node is as invocation expression. Invocation expression syntax. Yes. Okay, and then we know the expression of this is a member access. Var member access expression as member access expression syntax expression dot expression. Now we get a nullable warning here. Well, I did the type check up, so we can ignore that warning or suppress that warning here. Then we have then we need the generic name. Var name equals member access dot generic syntax dot name as generic syntax. Okay, again, suppress the nullable warning. We did check up above. Now we have the name. Okay, we got this one. That's cool. And actually, let's wrap that in a null forgiving expression. Okay. So we have the name and we need the arguments. We get that from the type argument list dot arguments. Var arguments equals member access dot, what was it? Type argument list. Oh, it's on the generic name. Oh, never mind. So it's on name dot type argument list dot arguments. Actually, we already know because we checked here. It can be only one. So let's directly get this single one in index 0. Let's get rid of this and use that one single one here. We already know that. Otherwise, the predicate wouldn't return true. And now we need two different things. Okay, so how do we do that? I will start with a naive approach. I guess there would be a better one, but I will create a new type. Private record class. I call it the name of invocation. And this has the syntax, the type syntax. I mark this nullable. This is the node. And we have a Boolean which says is full name, whether if we have the full name or the non-full name invoked. And then I returned it here. So new name of invocation. Actually, let's make this a struct. Name of invocation. We pass in the invocation, and this is the non-full, so this is false. And down there we return the full one, so this is true. And otherwise, if it's neither, if it's not the name of nor the full name of, we can return null here. Okay. Now we define that this one returns name of invocation nullable. Full name of invocation, yes. Okay, cool. Now our transform returns us name of invocation, but it may be null. So we may want to filter that. Oh yes, I can get rid of this T here. Excellent. Now we can also apply additional filters. So there is a set of extension methods to this I value providers. We could say where, provide an additional filter, where this, what's that? Our type, how do we call this? I call it element for now. Item. Item is not null. So we filter out the nulls. Oops. Oh, sorry, wrong file. We filter out the nulls that we kind of added here. Okay, cool. This is now our nodes. This is again the incremental values provider. So we need to collect that eventually. Let's see what else do we need. We can get rid of this now. If we have a look at the execute, again, let's get rid of all the syntax receiver part. What do we need? We have these, but we need the parse options. And we need as well the compilation. So we have more to combine. So let's first get let's do var compilation. Oops. Compilation and nodes, since we're about to combine now. So we say context dot compilation provider dot combine with the nodes, but since this is the nodes are incremental values provider and we need an incremental value provider, we are going to collect these. Excellent. So now we have the replacement of our syntax receiver in place, and also additionally put in the compilation. We need that. And we also need the parse options. So let's have another step. Let's get parse Pass. I call this now combined. This has now all 3 of them. We combine the already combined compilation and nodes with context dot pass options provider dot combine with these. And now I think we have everything in place. Let's have a look at the explicit type. We see this has all of them now. So this incremental value provider of type pass options, and this has now a tuple of compilation and nodes. Should this be called white? I call it other for now. And then we can, if the context dot register source output, have our source output action. This is a func. Let's create this method. And oops, I wanted to create a method. Was too quick. So now create constant. No, I want to create a method. No, okay. Cannot create a method with that. Why do I may be doing something wrong. Okay, guess I need to define it manually. Private void, we can make it static. My source output action. So what does this receive? This receives our incremental value provider plus the source production context. Okay, so we have the source production context and this incremental value provider. that's quite a type. Okay, and now we can basically move this logic up here and replace all the parts. Now I need a collection of the, how do I do this best? I start with a very naive way. This is not the most performant. I definitely got to replace this later on, but naive approach would be to just create this list. So that's a collection of I read only, I enumerable of type syntax, name of invocations is source.nodes, source.other, no, source.other.nodes, nodes, not what I'm doing wrong here. This is here my incremental value provider. Oh, it's not the incremental value provider. That's bad. It's of course the type itself. It's no longer value provider. We now get the type in. Okay. Nodes where the node is, well, it's not the node, this type that we have. Node dot it's this name of invocation. Yes, where the node. So we have here the nodes. This should be the nodes, yes. And this now value dot is full name. So we filtered these. Dot select node is node dot value dot node. This is not the most performant way. I bet there is a better way, but I will do this later on and do the same for the full name invocation. So we where we say, okay, so the first we filter all of them which are not full name and this, full name, and the other ones which are. Okay. Then we can change both of these methods to I enumerable actually. Or we changes also to I enumerable. Okay. Now we need to pass in the compilation. We have that in source dot. There's the compilation in source dot other dot compilation. There it is. Same for the compilation down here. And the last step we need to replace is the pass options. So we can say we have, where do we have the pass options? We have them in source dot pass options. Cool. Now it looks, there's one thing not compiling. Okay, I didn't set up this method correctly. So this method gets a incremental values provider. It gets an action of incremental value provider. Which one would I like to use? Incremental value provider and the action. Yes, my bad. I forgot to put in the nodes actually. There we go. That was my mistake. Now I can hit Control dot to create the method actually. Yes, now we have the correct syntax. I will copy that. Put it in here. Yes, and now we name it correctly. We have source. This is our context. We have our compilation. Now where am I? I put in the wrong one. I need to put in the combined, of course. So, sorry for this mistake. I put in the wrong step of the pipeline, basically. Okay, now we have everything. Now we have the context, pass options, compilation, nodes, other. We call this source. Now it compiles. And cool, now we can run the tests. And we would expect now the friendly name generator tests to pass. One does not pass. So the .NET 6 version doesn't pass, but the .NET framework, because I multi-target these tests. Source generated application. That's interesting. Why is my .NET 6 version failing? I don't know. Let's factor this a little bit. Okay, select here. Do we actually hit this? If I want to test. Okay, not implemented. Method or operation is not implemented. Do I still have? Okay, I have something not implemented. But I have. Okay, I believe this is again. This is not some issue with testing. I'm not fully familiar with Rider yet, but perhaps it works if I. So it seems that it tests an old version of the code. I actually had the not implemented exception, but I removed that. So I have the feeling it uses an older version of my code. Maybe if I just create a new test session, if this is the correct term. Yes, okay, now they're green. Here they are. Okay, it seems to have consumed old code. I will again do a brief mutation testing check. Let's see what can we change. Let's add string A here, just because. Let's run the tests. At least one should fail now. And none fails. Does it again? Maybe I need to again run the entire suite or create a new test session. Okay, we have one failing test with the .NET Framework version, not with the core version. Yeah, so there we have the diff where we expect private friendly, but we actually have private friendly of string. So test passes. I think I have some caching issues here. Okay, but it seems that the tests are running. So that's cool. And now there is one left. And then we perhaps have some time to check this link that I wrote. This is not the most optimal solution. Maybe we can briefly come up with a faster one. Oh, hello, Jason. Thank you very much for joining by. Okay, now the last one, the enum info generator, so the one which generates a faster version of enum get names, basically. Again, let's replace our syntax receiver first. No longer syntax receiver. I will partialize this one to become part of the enum info generator itself. Remove this, comment this out just for reference later. Okay, what we did before is we checked all the invocations, the argument lists, see that it only had one argument. Okay, so again, I will put this if statement. I will use this for the predicate of the syntax provider. So let's create our syntax provider. We say context.syntaxprovider.create syntax provider. We again have our syntax provider. The first one is the predicate, which filters. The second one, syntax provider transform, is the transformation part. Okay, let's create both. What was the shortcut that I just did? I really need to get more familiar with Rider. Create this method, yes, and create that method. Yes, I move them both to the partial class where the syntax provider used to be. We first have the filter, and in the predicate we put in basically this if check. Return boom. So this is where we filter all the syntax nodes. So every step should be doing filtering out most significant stuff immediately, and then filtering out, maybe from a performance point is more correct. We should filter out cheap and obvious stuff early, and then we can later on filter more expensive stuff that we are interested in. So here we only do like type checks and see if the argument list is indeed one and compare some names. So that should be rather quick. Okay. Now we have the context. Now we're in the transform. Again, we now need to convert this to some type. I used to have this enum info get name invocation. this is already a type that I have defined down here. Actually, I also want to change this into a record struct. So this holds both the invocation expression, so that I know whether it's name of or name, and the generic type argument as expression, that I know which type I should create this enum for. No, hold on. What do I need? This is not the friendly name. What do I need the invocation expression again for? Not sure. We will find out in a bit. Okay. So let's make this a struct. Record struct, of course. Oops. Records can't be sealed because cannot be inherited anyway. Okay. Now in the predicate, we now filter, and now we can transform this node. So we know that our node that we have here is indeed an invocation expression. Is as invocation expression. Let's suppress the nullable warning here again because I had the Boolean check up there. And what we previously did is basically invoke this code, put this up here. We use the method getArgumentExpression. And we need the arguments. Var arguments equals, how do we get the arguments? The arguments are in this invocation expression, argument lists. Those are the arguments. So we can get rid of this name, node.argumentList. .arguments. Yes, .arguments. Okay, and then we use to add to a list, we just now return this type. So we have here our invocation, and we return not t, but that. Okay, so we now replaced the syntax receiver. And now we need, let's see what else do we need so we can get rid of the previous syntax receiver method. In the execute or the former execute, we can get rid of all the syntax receiver code. Those invocations, we have them. Now we need the compilation. Let's actually do some to-dos here. We need the compilation. We need some way. This generator seems also to report diagnostics when something is wrong. We need a way to report report diagnostics. We have that. We need generator options. This is what I couldn't show earlier. We need to get so that's the analyzer options. Actually, if we go into this method, we see at some point we will say analyzer config options and get here this this value from the global config that I wanted to retrieve earlier or show changing earlier. And then we read it out whether it's true, set to true or false. And okay, we need the analyzer config options, and I assume that we can get them via the analyzer config options provider. So let's add this to the to-do. What else do we need? We need the compilation. Okay, we already want that. We need the parse options. Parse options, so we have them, and I guess that's it. Okay, so we have now a lot of stuff to combine. So first we have our nodes. Then we get our compilation and nodes. So I call it compilation and nodes is, we say context dot, we need the compilation so we can get the compilation provider dot combine, and we combine it with the collected nodes. Oops, collect. Great. And now we have the compilation. Now we need to add the parse options. So we now have parse options and compilation and nodes, because this always gets combined to another value tuple. So we say context dot parse option provider dot combine with the compilation and nodes we combined earlier. And one more combination. This is now the analyzer config options and parse options and nodes and compilation. Where we now get the context, we want analyzer config options, so there must be analyzer config options provider. Excellent. And we combine that with the incremental value provider we combined earlier to get yet another incremental value provider. And now we have everything combined, the pipeline assembled that we need. We can now go ahead and register our source output where this time I don't forget to actually put in those combined values and define our callback. We say source output action in lack of a more precise name. So let's give them proper names. We have our context here. We have our... Now what troubles me is... Oh no, everything is cool. We have our analyzer config options. We have the parse options. We have the compilation. We have our nodes. And since every combination, with the first combination, we create from a single value a value tuple. And with the next combination, we create then a value tuple where the white member again is a value tuple. And so we get always the white thing of this value tuple of 2 is again the previously combined. I call this other. And this is our entire source. Cool, and now we can move up the previous execute method from the Roslyn 4.8 source generator to this action from the 4.0 generator and basically replace all stuff that we now gathered. So receiver.invocations, those are our nodes. Actually, let's call them invocations here as well to keep compatible with the previous naming that I had. So this will be in source. Okay, now it gets a bit tricky. So this will be in source.other.other.invocations. Okay. Source.other.other. I believe I need better naming here. Where is the compilation? The compilation is in source.other.compilation. Okay. Source.other.compilation. No, it's not. I forgot one other. Sorry. Okay, the name is really bad. The options. We don't have generator execution context anymore. I need to get rid of that. So what we need is the analyzer config options. Okay, let's pass them in. Analyzer config options. That's the analyzer config options provider. Yeah. Okay, and let's pass that through. And up here we can now say source. Oops. Source dot. Where do we have it? There it is. And this one is in no other. So it's just the topmost source dot analyzer config options. The compilation we got previously, that's in double other. So we say source dot other dot other compilation options. Excellent. The parse options, we have them in source dot other. Ooh, I have a typo as well. Other. Source dot other dot parse options. Okay. Source dot other dot parse options. Excellent. And one more compilation error. We need to pass this in and replace this as well. One thing that I haven't fixed yet is here we need the context to report the diagnostics actually. So let's pass in our source production context all the way down to where we need it and pass it through here. And now we can again report diagnostics. It's now a different context, but this 4.0 context is just as able to create diagnostics as the 3.8 context is. Yes. And guess it's time to run the tests. Perhaps this time, let's do a .NET test via the CLI. Oops, I am just in the examples. CD, there we are. Yes, .NET test. Let's run all the tests. And everything is passing. No, one is failing. Okay, it seems that in one test I assume, because I now switched from the 3.8 generator, which is basically .NET 5. And in .NET 5, the default language version is C#9. But in 4.0 that we now switched to, we are in .NET 6 land. And for .NET 6 target frameworks, the default language is C#10. So I have somewhere a wrong default. Which test is it? Let's jump to that test. Okay. I'll for now just change this to C#10. And let's run the test again. Actually, let's also do a bit of an manual mutation test. So I browse through the code and find somewhere something that I could change. Somewhere a Boolean. I want to... let's check just here. So here I change this condition. I negate this condition, add an exclamation point, mutated the code, and now at least one test should fill. Let's see if that's happening. One test is failing. So we see that we expected something to be nullable, but it wasn't nullable. And the thing that we mutated was something within a has nullable reference types context. So that seems about right. If I revert that again and run the tests, now I should have everything green. Green, 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 and green. Excellent. Cool. So we now modernized from source generators, which, from 3.8 I source generators, which suffer from a performance issue in very big solutions. Well, not the generation per se, but in an editor experience. Still, on the CI level, there wouldn't. I'm not sure if there would. I guess there is no noticeable difference between using iSource generators or incremental source generators, because it does one full build. There is no incrementality to it, or when we build via the CI. But via the tooling, if one of our consumer of this generator has a huge project, now their experience would be better. So one last issue. Okay, we already worked 3 hours. Let's have a brief look at this one issue with the link, with the naive link that I wrote. If there is a more incremental way to do this. So this was in the friendly name generator, wasn't it? Yeah. Is there a way to do that? I presume there is, but I just don't know how. We could, since all those incremental value providers, they have a lot of extension methods, such as the where that I showed earlier. If I do a where here, actually, hope this was working. No. Where? No. Okay. does the where only work on the here? It seems so. Okay. But actually, what I want to show, let's have a look at the combine. If I have 12 this, there was a set of extension methods. So we have the incremental value provider extensions, where we can select values. We can select many, we can collect, we can combine, and we can also do a where. Okay, but the where we can only do an incremental values provider, not an incremental value provider. Okay, that makes sense. And can we like perhaps select this on a, would this make sense? To have those two, perhaps it would be better already from performance point of view to not have link, because the big issue that I cause here is basically I'm iterating through this nodes collection twice. Once with one filtering all the ones which is the full name and the others. So I guess this would be better already if we would. Is there refactoring to like do this into a naive for loop? But also there is refactor. Maybe there is. No. Okay, so a better way would be to actually for each this only once, and then perhaps let's have two lists. Var my name of invocations, name of invocations. Let's do a list. New. And another list for my full invocations. And we basically now have an if here where we do this check here. If, this is my node, if my node here is full name, then we add it to the full name list. And if it isn't, then we add it to the name of list. And of course we add the node value. Okay, cool. Now I only iterate through this list once. Actually, what I should have done is benchmarking to see if it really is faster. But I guess to benchmarking, I will come back. So benchmarking source generators, it's a little bit tricky. I haven't finally figured it out actually yet, but I will have in 2 weeks when I do the next session. And then we perhaps can have a look, then actually benchmark. This would be the perfect use case. What is faster? And I will also inspect if there is a more source generate incremental way to produce those two lists that are then split up. I guess I think I should basically rewrite this code a little bit, that I don't split it up in two methods which expect different lists. Just have one method which then does the if switch internally, so we don't need to do those filtering and splitting up. We can get rid of this entirely and basically then have just an if check down here which we select. I guess this would be then better, but I need to rewrite a bit of code that I will do at a later point, because this is not necessarily source generator related, but the general performance thing that I need to improve here. But other than that, I have a look at our agenda, and I believe we are quite through, aren't we? I will briefly recap the agenda. If there are any questions, then please put them in, and then I could come up either immediately with an answer or maybe follow up in the next session. So we had a look at what source generators are, why and when we want to use them. So to produce reflection-free, fast, potentially naive, repetitive code. And so the user of the source generator doesn't need to maintain this code because the source generator takes care of that. We learned the limitations. So generators cannot depend on each other. They need to be net standard 2.0. And they can only add new sources, not modify existing source. We'll look at the two C#9 features that facilitate source generators, especially the partial thing, which is heavily used by the generators that the .NET team is creating. We had a look at some of the generators which are included in .NET 6 already. We also had a peek at the regex. The regex generator. I will put a link here later on. We'll look at how we can test source generators, very similar how we test other Roslyn related features such as analyzers, code fixes, and so on. We had a look at a 3.8 generator. We saw the post-initialization context, which has been added in 3.9. By the way, an incremental source generator still can do this post-initialization as well, actually. Can it? It should. Let's see. If I say .post, yeah, there's a register post-initialization context output, post-initialization output as well. So this feature is still supported with Roslyn 4.0, the .NET 6 version of source generators. Okay, we had a look at this. We saw so the real benefit of source generators is that they are faster in an IDE experience when the user is actually constantly typing code, and then less nodes are analyzed and less of generator code is executed. The drawback is that perhaps the programming model, at least for me, is a bit less obvious, since with all the combination that we do here, I'm unused to this programming model. I guess in a year it will be just as writing any other code. So perhaps the learning curve is a bit higher. It's not like that generators or Roslyn in general doesn't have a high learning curve already, but this is maybe for me even a little bit higher. And then we live coded, we modernized some source generators into incremental generators, and this is indeed a breaking change. Now, when I release this package later, it only works in .NET 6 SDK, and so if I would build this project in a .NET 5 SDK, the source wouldn't be generated. And then if I have a partial implementation, the implementation would be missing, and then the user code wouldn't compile. And last step, upcoming streams. If I scroll to the bottom, let's do another Let's Code session in 2 weeks again. So this is my general fortnightly. So on the 5th of March, again, 1300 UTC, I will again stream about source generators. I love source generators. This time we will be building a new incremental source generator from scratch. So we won't convert anything existing, we build a new one, test-drivenly, all anew. And another thing I have, it's next Wednesday over at the PostSharp channel. I'll be giving a webinar on Roslyn generators. So this will be a more condensed version of what we had a look at today. Cool. Then in this document, I also linked some resources. So there is, let me close. Can I close all tabs? Yes. So I linked also the source generator cookbook. So if you want to get started with the 3.8 source generators, this cookbook basically contains, this is how I also got started, and watching some talks that are also linked, where everything is basically shown. For example, how we can test source generators by using these packages, and how those analyzer config options, how we can access config options basically like this, and how we can consume. For example, we could have, so one thing is if we want to if we want to expose MS build properties to source generators or to analyzers in general, we need to make them visible to the generator. So we must say compiler visible property, and now a property which has this name is visible to the compiler and can be, with that syntax, be consumed by the generator. And here we have the thing again, this context, analyzer config options that we saw previously, and more. This also explains how we can consume additional files and so on and so forth. So this is a very good starting resource. Also link both the proposal for source generators and incremental generators. Unfortunately, or at least I couldn't find any cookbook kind of complete documentation for incremental generators yet. I guess there is some, but I haven't found it yet. I linked some projects of source generators, if we can look at them. So there is this NuGet package, this GitHub project, which lists a lot of generators. There is a lot. So maybe you can make use of some of them and get rid of some tedious reflection-based code already and improve the runtime of your code. There's another repository. We have researched also a couple of generators. And for example, there is somewhat recently, I think a couple of months ago, the community toolkit was released also with a generator. In that case, an MVVM-based generator. If I find that code, where is it? Is it in compiler services? Where would that one, or is it in here? Where would the generator be? Look at MVVM. No? Source generator? Okay, basically I wanted to show, I think they have implemented an iNotify property changed generator. There is multiple. There they are. There it is. The iNotify property changed generator, which basically generates iNotify property change implementations for you. I think this works like you put an attribute on top of your partial property, or is it not sure. But for example, this is how you could generate tedious implementations for iNotify property change via generator. And if you would like to know more, there is a lot of content in the web. I just listed a few. This is the talk by David Vengier. This is the first Roslyn generator talk that I watched myself. There's one by Andre, which is in the .NET Dev, in the JetBrains.NET online days. We have, this was the one actually that inspiring me eventually to have a closer look at generators by using source generators for fun by Jason Bock. This one is my personal favorite because this is how I started with source generators. There is one by Martin Ulrich. He also dives a little bit into the incremental generators. I gave a talk at NDC Oslo, and the one that we had a look already by Chris, which dives deep into how incremental generators work. So there is a lot of more content. And yeah, I'm having a brief look at the chat if there are some open questions, or if I perhaps forgot to answer one. But for now, it seems all right. If you have a follow-up question, then please, you can comment in here, and I'll follow up on that. And otherwise, we will see perhaps on Wednesday, or maybe in 2 weeks for my next Let's Code fortnightly. So with that, thank you very much for staying a while and listening. In 2 weeks, this will also be on YouTube. If you are interested, I will then announce the YouTube channel and such. And yeah, this is basically everything that I know about source generators so far. And in 2 weeks together, we will produce more source generator know-how. So thank you very much. Take care. Goodbye. I wanted to show this one. Yes.